So hello, thank you everybody for having me here. I'm Umberto Maio from the Italian Institute of Astrophysics at the Observatory of Trieste. I'm briefly giving you a short highlight of some recent work which I've been doing over the past few years concerning numerical simulations of primordial structures. In general, if you want to try to model primordial structures like primordial stars and primordial galaxies within cosmological simulation, so you need to include a number of ingredients in your modeling, which are not always found in standard large-scale simulations, as we've seen also yesterday. In particular, first of all, you need to include the molecules, because molecular evolution and molecular cooling is the main driver of gas cooling at early times, because at early times you have no metals, and you can only rely on H2 as a relevant coolant. Then, once you form metals, you can form subsequent POP2 stars and the following generation of stars. And for doing that, you have to follow stellar evolution. This means that you have to include in your modeling emission from yields from supernovae type 2, AGB stars, and supernovae 1A. And these are not negligible processes, because supernovae 1A explode after about 1 gigayear or even less. And therefore, at redshift 6, you might have already supernovae 1A events and AGB events, not only supernovae 2. So supernovae 2 are not sufficient to explain metals at high redshift. Of course, you can play with stellar evolution parameters and properties and modeling when you model your simulation. And this is what I've been doing for a number of boxes with different sizes and particles. These runs were originally made with Gadget, various versions of Gadget, but they are essentially SPH simulations. And you find very interesting results, which I will summarize here, starting from the latest ones. The latest ones is about carbon plus emission, because in this modeling I am including cooling from low temperature gas. In particular, I'm explicitly including carbon plus emission in the simulations. This means that for each gas particle, one can actually compute carbon plus emission from temperature and density of the gas, so without relying on calibrated fits, which usually are based on star formation rate. And in this way, you can really perform a sort of intensity mapping at different redshifts, and we perform these studies. These studies are redshift between 6 and 14 or so. You have the reference there if you want to look at the trends of carbon plus, at the theoretical trends expected by these simulations between carbon plus emission and star formation rate, stellar mass, H1 mass, H2 mass. And these quantities are all computed independently, so they are not linked each other for the purpose. And of course, you can study with this modeling also different POP3 diagnostics. So since POP3 stars are really difficult to be observed, you might rely on the yields emitted by stars from different masses, and this gives you a huge parameter space where you see those lines. These lines transition where metal diagnostics can indicate POP3 or POP2 star formation for different metal abundance ratios, like silicon over oxygen, Phi over carbon, carbon over oxygen, and so on. Of course, this depends on the yields you adopt. And then, of course, I have shown several times that you can have these POP3, POP2 transitions at early time, but this is kind of parameter dependent, that it's not easy to get final conclusions on the actual results. However, this was the very first study I did back to 2010-11, later on I performed more tests, but what you see is that usually in these cases you are strongly limited by numerical resolution and the box that you use. And finally, you can even try to have hints for direct collapse black holes, which is another hot topic and is which is highly dependent on your modeling. And for all these studies, I mean, you might look at the references here, and of course there are many more topics which can be explored at high redshift. Some of them are listed here, but I mean, I will stop here for the moment. Thank you very much.
Thank you, Umberto. We have no questions for the lightning talk, but you may take the chance to discuss over coffee.